So all these problems we've done, trying to find maxes, mins, test points, those are our critical points, and those always occur when the first derivative is either 0 or undefined. Something's going on there where we have a horizontal tangent or some sort of issue in terms of making it undefined. Okay. Then, where we have extreme values, the first two we're going to list are the critical points. So those certainly are places where we're concerned about. So that's going to be first derivative is 0, first derivative is undefined. Those are places where we can get our maxes and our mins. And then the third thing, we don't consider them critical points, but there's certainly places we can get our biggest or smallest value, and that's at endpoints if we have them. All right, those two we've done endlessly. We've done that a lot, so hopefully that's nothing new. 3, we dealt with what's called the extreme value theorem. Extreme values just meaning maxes and mins. So it's a theorem that guarantees maxes and mins as long as your function is continuous on a closed interval, then you have to get a maximum value and a minimum value. There's no way we cannot. So we must have a maximum and a minimum value. Right? There's no way we couldn't. So if we look at these guys, we won't necessarily go through all of them just to save a little bit of time. But if we look at this function here, this is a continuous function by itself. There's no issue with a parabola that opens upwards. If we look at letter A, it's a closed interval. So think about what this graph looks like as a parabola that starts at a -1. Our vertex would have been at 0, 2. And then if we come over here to 2, 4. So just visually, if we look at that graph, there is very clearly a low point and a high point on that graph. Okay. So what we did in terms of the work, this is where we identified what our candidates were. On the quiz, a number of us didn't include the endpoints. So if you did go back and look at your quiz, that's one of the mistakes that some of us made. So those are definitely candidates. Some of us on that quiz just jumped right to the derivative. So if we took that derivative, so y equals 2x, you look to see if that's undefined anywhere. All right, it's not undefined anywhere, but we can still set that equal to 0. And when you solve that, the x value was 0 is a candidate. On the test, be very, very careful of this. There's going to be a lot of multiple choice. Know what I'm looking for. So this is the extreme values of the function. So that's what I'm looking for, values of the function. So what we're ultimately concerned about are what is the biggest y value, or what is the biggest y value, what is the smallest y value. So we don't really need to set up sign charts when we did these. We're not concerned about the x coordinates. We want to know what the y values are. So figure out your functional values. This should have been 3, f2 is 6, f of 0 is 2. And with this being a lot of multiple choice, let's say I wanted a max. So don't fall for this. I'm trying to tell you right now to be aware of this. When you take this test on Wednesday or Friday or Thursday, one of the answers is going to be a 2, one of the answers is going to be a 6. So you have to know, what am I looking for? Am I looking for where it occurred, at what x coordinate does it occur, or are we looking at the y value? Because very clearly, this is somehow our answer. That's the biggest y value. And if I'm asking the question in this way, the values of the function, then we need to make sure that we are picking the 6, because that's the largest value of the function. Okay? If it's the one where you show work, that's what I did on the quiz. You would tell me the max is the y value of 6. And then you would tell me the min is the y value of 2. That's how we wrote it on our quiz. You're going to get a lot of multiple choice though on this test. Okay, so know which one I'm looking for. Now, the next one, we won't go all the way through it. Think about what this one looks like. There's an open dot at -1 now. Looks like this. And then same thing over here at 2, there's an open dot. All we have in this one is a minimum. This is the lowest point on our graph. We do not have a maximum, and you weren't guaranteed a maximum, because the only way the extreme value theorem guarantees something is if you're continuous and you're on a closed interval, and we are not. Okay, so know the extreme value theorem now pretty well. I can tell you one of the questions in the test that is commonly missed year after year is this test, and people kind of miss an element of this. All right, so just know that you have to have a max, you have to have a min if it's a continuous function on a closed interval. All right, and then that was pretty much 4-1. That's when we first introduced critical points, where the derivative is zero undefined, where can we get maxes and mins. And then we went to 4-3. And one of the things we talked about is what's called the mean value theorem. So the mean value theorem, so it's another theorem, similar conditions. We have to be continuous on a closed interval, just like the previous extreme value theorem said, continuous on a closed interval. For the mean value theorem to hold true, we also need to be differentiable on that same interval, although we're not necessarily worried about what's going on at the endpoints for the derivative. So what that means graphically, because I could very well test you on this graphically as well. Put A here, put a B over here. And what I had you do the time we did this in class, I said start at A, end at B. You really could put those points anywhere you want them. I said connect them any way you want. So I'm going to do this as long as we're continuous and differentiable, as long as we're satisfying this idea and this idea. So no sharp corners, no discontinuities, nothing crazy. And what the mean value theorem is saying is that somewhere the average rate of change must equal the instantaneous rate of change. So graphically what that looks like, the secant line, if you remember, is the average rate of change line. So whatever the slope of that red line is, that's the average rate of change. Since I have a graph that's continuous and differentiable, the mean value theorem will guarantee there is at least one other point on the curve where the tangent line has the same slope. So for me, if I go to right about here and I sketch in a tangent line, that blue line would have the same slope as the red one. However, like many of you at home, hopefully, who drew this in, I have another one. If I go to right around here, wouldn't I be able to draw in another tangent line that has the same slope as the red one? So in this case, there's two. Okay, so as long as I'm continuous, as long as I'm differentiable, we're good to go. I think I showed this class because I think I forgot to tell fifth period, but I did tell you guys the AP question from a couple of years ago where they gave them like 0 to 10, and they asked, does the mean value theorem apply to this problem from 0 to 10? So here's my average rate of change. Is there any other point between 0 and 10 that has that exact same slope? And the answer would be no, because this has its slope. That's not parallel to the red line. This has its own slope, not parallel to the red line. So the answer was no, and the reason for that is it didn't satisfy this idea here because of that sharp corner. All right, so it has to be continuous, has to be differentiable. That's what it looks like. Yeah, go ahead, Ethan.
Oh, real quick, can you go up to the one where it's on the closed interval, -1, 1? Just it was like up, like.
Yeah, here.
Yeah. So the extreme value theorem is like that. There's always going to be a minimum and a maximum. I see the minimum, but.
Okay, there's always going to be a maximum and a minimum if we're continuous. So this is a continuous graph, but we also have to be continuous on a closed interval. Is this one on a closed interval?
Oh no, because they have it's not closed yet.
Correct. So you're right, because if those two things are true, you must have a high point and a low point. But because you just told me that this right here doesn't actually happen, we don't have to have a maximum and a minimum. All we have in this one is a minimum. So if I did ask this question, you would say the minimum is still that y value of 2, just like it was over here. But if I now ask you the max, you're 100% correct. You would say there isn't one. And the extreme value theorem wouldn't have guaranteed us one because it didn't satisfy the two conditions.
So if it's not closed, then it could either have a min, a max, or neither?
Correct. Yep.
Okay.
So like this one, you better get both because it's a closed interval. This one, we could get both. We could get none. We could just get one like you just said.
All right, thank you.
Yep. All right, so let's finish this guy off at least. We're only one problem behind. So what this looks like algebraically, if we actually have to do our problem, the average rate of change is nothing more than your slope. So it's our change in y over our change in x. So the way we write that is f of 1 minus f of 0, because that's just the interval that we're talking about here, 0 to 1. That's the change in y's, and then divide that by the change in x, 1 minus a 0. This is pretty easy in terms of getting these values. So take a 1 and plug it in. 1 to the 2/3 should be 1. A 0 to the 2/3 should be a 0, and then over a 1. So my average rate of change is 1. So our average slope, if we connected the two endpoints, the slope is a 1. The instantaneous rate of change is nothing more than your derivative. So you're now going to take that derivative. So that would be 2/3 x to the negative 1/3. And we'll clean that up a little bit. So 2/3. The negative exponent is going to get put into the denominator so that it becomes positive, and it becomes a cubed root of x. And we have our equation now. So let me do the work over here. So we're going to take that 2/3 cubed root of x, and we're going to set that equal to 1. Uh-oh. And I just lost a 3. All right, so then what I'm going to do, I'm going to multiply both sides by the cube root of x. So it cancels here. I get a cube root of x over there. So now I just have a 2/3 equals a cube root of x. Cube both sides. And we better get an answer between 0 and 1. So we get 8 over 27. I can't tell you exactly what that decimal is, but I can tell you that it is between 0 and 1. You can get more answers, right? If we ever get like a plus minus, there's ways you can get more answers. I just showed over here with the graph, we can get more than 1. So that's certainly viable if that does happen. Okay. All right. It's probably about as far as we're going to go. I do want to do 6, so we'll start that tomorrow. And then, like I said earlier, we'll do most of this packet together. If you want to kind of look at the other ones in preparation for Wednesday, those you're going to probably be left on your own. The answers are on Canvas as well. So as you're working, if you wanted to go through those, you can kind of do a check every problem or so to make sure that you're on the right track. Okay. But with that, we're going to stop. We're not going to get anything else done in 2 minutes. So just have this ready to go tomorrow, and we'll pick up from here starting tomorrow. All right. See you guys. Have a good night. And Veronica, just hang on until everybody's gone from class too. Yeah, go ahead, Pranav.
All right, so for the extreme value theorem, if x
Pranav always breaks up on me.
and try to find the maximum or minimum.
Pranav, I heard the first couple of words and then the very last couple of words. Say that one more time. Extreme value theorem, I heard.
So for the extreme value theorem, if you drew a straight horizontal line from A to B,
Yep.
wouldn't that mean you couldn't find a maximum or minimum?
Pranav, you're killing me right now. Yeah, that's what I had you guys do. If you went back to the notes, I had us kind of sketch a few of these out, and then the third one I asked you to try to contradict this because people kind of think that way, and it's a legitimate thought. But what I then did is I talked about how, let's say that's the graph you're thinking of. Is that fair enough? What you just told me?
Yeah.
So 1,
Yeah.
2, 3, 4. All right, so if I now ask you these two questions, what's the maximum value of y? What would you have to tell me the largest y value that graph achieves is?
4.
4.
Well, I remember this.
You do?
Yeah, it's where you have both a minimum and a maximum at the same point.
Right. It was. I now remember this too because Kevin was the only person in school that day or the day
I
before,
remember.
and he was the tallest person and the shortest person all at the same time. So yeah, it's sort of a trick, but yeah, you can definitely say there is a high point and a low point.
Okay, thank you very much. I was just wondering.
Yep.
Have a great day.
Yep. No problem. All right.
Mr. Pena,
Yes, sir.
on the quiz, is the reason I like.
All right. See you guys. Have a good night.
Is that because I left it as a fraction?
I don't know. Let me look.
I'm pretty sure I'd have to, else I divide it by.
Let's see. All right, try in here. We're a little slow. Let me try to stop recording too. That always slows me down.